Hello everyone, this is Vasant, a 9-pointer at IIT Bombay from the Department of Civil Engineering. In this video, we are going to discuss about pure bending. This is the third part on this pure bending topic. So, first we are going to derive moment curvature relationship. See, when you apply a movement, it is responsible for the bending, right? So because of the bending, the curvature is getting developed, right? So can we relate this moment applied and the curvature? Yes, we can relate those two things. So we know that at a cross section, if you see at a cross section, the bending stresses will develop, right? The stresses developed to the bending, the normal stresses developed to the due to the bending is known as bending stresses. Okay. So because of this applied bending moment, because of these moments applied, there will create at every cross section, there will be some value of bending moment, right? So that bending moment at that cross section is responsible or is causing the normal stresses at that cross section, right? So these normal stresses are result of the bending moment at that cross section. So the net movement created by these normal stresses should be equals to the bending moment, which is the cause for this normal stresses, right? So the net movement created by the bending stresses is given by sigma x into dA is the force, right? If you take a cross section and suppose this is the neutral axis, this is x and this is y, and if you take a small element dA, suppose at that for the dA portion, the value of bending stress is sigma x, then sigma x dA will be the normal stress which will be perpendicular to that plane. So the force will be like this, perpendicular to this plane. The force will be perpendicular to this plane, right? So the bending moment will be that force into this perpendicular distance, right? So this perpendicular distance is y. So sigma x dA into y. That is causing clockwise, but we take anti-clockwise as positive. So this is negative, right? So this is dm. If we integrate on whole area, we should get bending moment at that cross section. So the bending moment at that cross section m is given by what is the value of sigma x, that is minus e into kappa y, right? So from that we get kappa into e y square dA, right? So we get kappa into e integral a y square dA. This will be equals to I, right? M is equals to kappa into ei. This I is known as area moment of inertia. Okay. See, if you observe, in torsion case, we get J, that is also area moment of inertia, that is actually known as polar moment of inertia. And in some cases, we get I. So we need to understand about which axis we are calculating the moment of inertia. So while in the torsion case, the torsion moment will be like this, right? So the direction that the vector representation of this torsion will be like this, right? So that axis will be perpendicular to the cross section. So about this axis we calculated the J. About this axis we calculated the J. Similarly, now if you are bending like this, if you are bending like this, so you are bending like this, right? So if you are bending like this, what is the vector representation of this moment? From right hand thumb rule, we get like this, right? So it is towards me, it will be towards you. Okay, it will shows reverse, right, in camera. So it will be in this direction, right? So the axis is like this for this bending moment. So the I which you calculate should be about this axis. Okay, if you apply bending moment like this, then also it causes deformation, right? Then also it creates curvature. So now you applied bending moment like this. Okay, now you applied bending moment like this, so the axis will be like this. So for that case, the I should be calculated for this axis. Okay, that you should understand carefully. So from this we get kappa curvature will be is equals to m by EA. Okay. So we know that for pure bending, the bending moment will remain constant. So this m is constant. And for prismatic bar, the value of E and I will also be constant, right? Means for prismatic, homogeneous and isotropic material with single homogeneous and isotropic material, the value of EI will be constant for that given beam. So M is constant and EI is constant. So the radius of curvature is constant in case of pure bending. Okay. That you need to understand. Okay. So this is about moment curvature relationship. Now there is one more formula that is known as flexural formula. See, we already know kappa is given by m by EI, sorry, right? And we already know that sigma is given by minus kappa into E into Y, right? So if you substitute value of kappa in this sigma, you get sigma will be is equals to minus my by I. So this is known as flexural formula. So these bending stresses are also known as flexural stresses. Okay. And this EI, whatever is there now, this is known as rigidity, flexural rigidity. Okay. Right. So this formula is made sigma x is equals to minus my by I. Again, consider only magnitude and by intuition put the sign. See if you apply positive bending moment like this is positive bending moment because it is anti-clockwise. So upper there will be compressive stresses, lower there will be tensile stresses. Suppose if you need to calculate bending stress at this point distance y from this neutral axis, then you know that the magnitude will be given by my by I. And from intuition, we also know that the value is compressive. So from intuition, you can put the sign and just from formula just calculate the value. So just remember that bending stresses are given by my by I. Okay. This is about flexural formula and maximum stresses. It is clear that the strains are varying like this. If you see the formula also, sigma will be is equals to my by I. M is constant for a cross section, I is constant for a cross section. The only variation is y. So y is from neutral axis. So this is neutral surface. So this will be y. So for this positive bending moment case, the maximum compression will occur over here. Here there will be maximum compressive stress. Here there will be maximum tensile stress. If you only consider in terms of magnitude, suppose if this distance is y1 and this distance is y2, so if y1 is greater than y2, then this will be overall maximum if we only need to consider the magnitude. If y1 is less than y2, then this will be maximum, right? Understood? So from this there is they define one term that is known as section modulus. So if you see the maximum will occur at C1 by I1, and if you write minus I by C1, that is Y1, okay? This is C1, this is C2. So this I by C1 is replaced by S1. This I by C2 is replaced by S2. These are known as section moduli, okay? So these two values are different if C1 and C2 are different, right? If C1 and C2 are same, then they are same. So when they can be same, that can happen in case of doubly symmetric shapes. So if you see over here, this is a rectangle, it is doubly symmetric. So the centroid will pass through this. So the neutral surface will pass through this. The neutral surface will pass through this like this, something like this, right? So the y, the maximum y over here, C1 will be is equals to C2 over here, that is h by 2, right? So in this case, C1 will be is equals to C2, right? So in this case also, if you see, this will be d by 2 and this will be d by 2 and O is centroid, right? So the maximum stresses are same here and here, but there is change in sign, okay? Difference in sign. So again, C1 is equals to C2. So here there is only one section modulus, okay, that is given by I by C. So this will be is equal to some value C, this will be is equals to some value C. So this is I by C. So before going ahead, we need to understand the values of area moment of inertia for different shapes, okay. So if you take this this one, and you are, this is the rectangular beam, you are applying like this, then the axis about which you are need to calculate the I is this one, right? So that is like this one, right? So for this axis, what is the moment of area moment of inertia? See, if you know, if there is a rod and there is a this one like this, then moment of inertia, mass moment of inertia is given by, suppose this length is L, that is given by ml square by 2L. So in case of area moment of inertia, just replace it by area, man. So for this axis, the area moment of inertia will be equals to, what is the area? Area is B into H, and L is also H square divided by 2L. So the value of I will be BH cube by 12. Similarly, if this is a circular cross section, you are applying like this, then this axis will be for calculation of I. This is the axis for calculation of I, right? So if you know, for a disc is like this, and perpendicular to the plane, the axis is there. Then for this, the mass moment of inertia is given by mr square by 2, right? And if you take this one, for this one, the mass moment of inertia is given by mr square by 4, right? So this mr square by 4, if you need to calculate area moment of inertia for that same axis, then replace mass with area. So area is pi r square. So pi r power by 4 by 4, that is pi d power 4 divided by 64. Okay. This is how we will calculate the area moment of inertia at different axes, for different axes. Okay. So with this, we end today's lecture, and we completed the theory part of pure bending, and we will solve some numericals to understand these concepts thoroughly. If you like this lecture, do subscribe to our channel, 9pointer. Thank you.